First, I'd like to thank the organizers for inviting me here. It's exciting to be on campus of Columbia University. I've never been here before, but I've heard of it many, many times because it was my wife's dream to go to grad school here. It did not work out, but at least I heard what a wonderful place this is. Let me start in prehistory. Transmission of scientific knowledge, or even more generally, the knowledge of how the world works, has always been done orally, from mother to child, or from, to the neighbors or the members of the tribe. Don't tease the dog when he's eating. Those kinds of things have been transmitted orally, and are still transmitted orally. That's why this building has this very room for oral transmission of scientific information or knowledge information between members of the tribe. Now, when I say members of the tribe, we can go back to prehistory again. A tribe that has the knowledge of how to start a fire instead of just steal one, or how to make a superior bow and arrows, is going to have a serious advantage over the other tribes. And that advantage can be measured in lives and deaths. So knowledge has power, and real world power. So secretiveness about knowledge is something that we've had with us for millennia, because whoever possesses useful knowledge has advantage over the competitors. So it is not surprising that a more narrow scientific tribe was quite secretive for a long time going. This guy, and he's huge, but we can make him smaller, is Newton. He and many of the great scientists of the old ages, they did not publish in scientific journals. They did not say anything out in public because for them, knowledge was power. They were either personally rich or they had rich sponsors. They could afford to spend 10, 20 years building a humongous theoretical construct, which then gets published in a book. And at that time, publishing books was not easy or cheap either. You had to be well connected or rich or have a rich sponsor in order to publish a book. Once you publish a book like Principia, well, that's a monument to your intellect, and that's how you become famous and maybe rich from the sales of the books because they're expensive. So at the time when Newton and some, and the others were publishing, and that is 17th century, see, 1686, Principia was published as a book. And Newton didn't like the idea of having journals. This is also 17th century. The 17th century is pretty much the beginning of the journals. It was a radical idea. That was open access of the 17th century. People like Newton did not like the idea at all. They were fighting it tooth and nail. They wanted to keep their secrets. Why? Because knowledge is power. And they're very, very privileged members of the society. Not everybody could afford to be a scientist. It was a very small tribe. Having journals out meant that a lot more people could do and publish science and get maybe a livelihood from it, maybe fame from it. But the mode of doing science then became different because you could do a couple of experiments and publish immediately. You don't have to construct an enormous theoretical construct that fits in a book and wait 10 or 20 years until that's done. You can kind of go along as your research is progressing. You can report on that as it goes, one experiment at a time, 3 experiments at a time, and tell the world about what you're doing. The whole movement of starting journals and it's similar to what's happening today, was really a relatively small number of people having a vision and then pushing for it really, really, really hard. Because they had to deal with Newton, who didn't like it, and they had to deal with some very, very powerful forces against journals, against scientific journals as a concept. This is not how science is done. Science has to be secretive because science is power. So the journals did prevail after a while, and it became a norm. It changed the world as science was done. Instead of working for 20 years and publishing a book these days doesn't really mean much. It's kind of a side project for you. Oh, you published a book? Cool, cute. Your scientific career is measured in your publications in a journal. Right now, we are in the midst of, let's say, a second transition. In the openness. While the initial journals in the 17th and 18th century democratized science as much as they could at that time. What they could do is print. They had printing presses. And that enabled a much larger number of scientists to become known, prominent, published, to get jobs, to get promotions within their institutions. It wasn't really global and really democratic, but much better than what it came before. Now we've had the World Wide Web for 20 years now, or something like that. And the web is really changing everything we do. It's really globalizing information. And this is having some big effects on the way science is communicated, and this, I think, is going to change the way science is done. Just like the first, let's say, revolution in scientific communication has moved from making overarching enormous theories that take 20 years to build into smaller snippets. I think this, the transition that we're going through is also going to change the way we are doing science, not just publishing it. What I mean by that, this is a slide, a picture that I shamelessly stole from Michael Nielsen, who's up at Perimeter Institute in Canada, who wrote an absolutely wonderful essay about it. He's writing a book about future of science, and a lot of ideas I stole from Michael. Or sometimes we had the same idea at the same time. It was like, okay, great minds think alike. Every change, every revolution in technology that affects the way science is communicating does is expands the proportion of the useful knowledge that becomes shareable. Shareable means I can tell you and you can tell me, and or we can all read it. More people can read it. More people can find it. Which is an important thing to think about, that the first journals, what they did is they could publish scientific papers. Today, with the web, we can do more than that. There's not just scientific papers. There are many other ways of sharing scientific ideas, scientific data and information with others. So there are scientific papers, which are kind of a final version of a story containing several experiments, the idea or the conclusions coming out of it. We now have preprints. It's pretty easy and cheap to put ideas up there before they're completely digested and done, and people then from around the world can come look at your stuff and comment on it and say, hey, maybe you should try this or try that. I think that you're wrong about this detail. So it's kind of a work in progress, and once it's done, then you can submit it to a journal and it becomes a paper. Data. Data usually set in hand-drawn notebooks. And I'm not going to steal the thunder of the people after me, because they're going to focus much more on that. The data, the notebooks, all of those things can be easily now placed on the web and thus shared freely. So if I publish a paper which contains a large data set, somebody else can come in and look at the data and crunch it in a different way, pass it through a different piece of software, see what it comes out, adds another idea, mesh it with something else, or use the same, let's say, method that you use on a different data set and see how it compares. This allows many more people to use the same data set in a useful way, which speeds up the progress of scientific knowledge. Video is another thing. You can't put video on paper. You can't put video online. Many of you here are working scientists, or used to be, and you try to do something in your lab, and you are reading materials and methods section of a paper, and you try to replicate. That's what materials and methods section is for, to allow people to replicate. Did you actually manage to replicate? No, there's always missing information, and it's always not always easy to understand what was really done there. There's a lot of tacit knowledge that is passed from advisor to student over generations, over and over and over again, never shows up in papers. How can you learn, let's say, a technique that you want to use in your laboratory? Video provides a great way of doing it, because video is going to show you things that the person doing it is just never going to think about. You know, of course everybody knows this is how it's done, this is how you decant. But what if somebody is a novice and doesn't know how to decant? You see that on the video. It's not written in materials and methods, but you can see it. You can see how it's done. So a lot more useful knowledge can pass through uses of new technologies like video, audio, or data that can be automatically put in your software, reanalyzed in different ways. For all of this to happen, the data have to be free. One thing about the journals is that they are printed. Paper, ink, print presses, trucks and drivers who drive them, that's very, very expensive stuff. Putting stuff online is very, very cheap. You need to buy a computer, okay, $1,000, or you can go to the library and do it. It's really, really much, much cheaper to put stuff online, and no need to charge for it anymore. And if you don't charge for it anymore, then everybody can access it. Now that is really democratizing, because it's not just that, you know, Newton and Galton and those people can exchange information with each other, or people at big universities like Columbia can see it because their library put many, many, you know, thousands and thousands of dollars into journals. But a scientist in a budding scientific community in Morocco can also read the same thing, use the same data, see the same video, and promote him or herself because he's smart, has good ideas, maybe doesn't have the infrastructure at home to utilize, to actually do what needs to be done, but he can get in touch with others who can and collaborate. So it's really democratizing in the sense that it's globalizing. You don't have to be at Columbia or Harvard or MIT or anywhere else in order to become a good scientist and enter the world of elite science. You can be wherever you want. You can be at a small community college. You can be in high school. I mean, a high school teacher or something like that. You can be in a developing country and still, if you have the smarts, you have the interest, you can contact others. You can connect with others. You can reanalyze other people's data. You can come up with great ideas and start collaborations and test those ideas, even if your country or your school doesn't have the money to pay for journals or the infrastructure for you to have all the laboratory equipment that you need. So I'm putting Science Commons out there because they're really promoting the ways of sharing the information, coming up with licenses, how to share information free with everybody who's interested in it, regardless of their socioeconomic position, their employment, or the country of origin. Opening research, so two people after me, they're going to talk about their ongoing efforts. But it's pretty important to be able to see what's already been published. And that's where we come to open access. Open access movement is a movement to try to make all the published research, which means the finalized papers, made free, available online. And here we have some terms we have to make clean. Free access means you don't have to pay. When you go to the website, it doesn't ask you for $60 to see a paper, which is really, really important, especially if you're in a country where $60 is an annual income. The other thing is open access. True open access allows you not just to access it for free, but also to do stuff with it. You can translate it, you can reanalyze the data, you can copy and paste and write a blog post about it without having to pay anybody for copyright. All you need to do is to say, this is where I got the data from this paper. You link back to it. There's a difference between free access and open access. Another two terms that differ are green open access and gold open access. Green open access is what libraries do. And that means when a paper is published, the copy of it gets posted on a library repository or institutional repository, which is then made free for everybody to access. Gold open access is actually an open access journal. You submit the manuscript to an open access journal. The moment it's published, it's free and open for everybody to see, download, mash up, translate, redo, whatever they want to do with it. Those two are often presented as in clash with each other, but I don't think so. I think they actually work together well because there are pros and cons to both. One of the for me at least, the big pros of green open access is that you can go back into the past. If you publish a brand new paper in PLoS biology, for instance, it's brand new research. But often we need to dig back into the past, into the papers that have been published 20, 50, 100 years ago. Repositories are slowly going back into the past and capturing that historical knowledge which otherwise will be forgotten. And it's important knowledge base that we have to work on and work with. That's for me the biggest importance of the green. The gold open access or open access journals, the thing is immediacy. There's no need to wait 6 or 12 months to get the paper published, and it's immediately out there. Now, I work for PLoS. I have to do a little PR for PLoS. This is one of the papers in PLoS 1. PLoS 1 is an experimental journal in the sense that it doesn't have a theme or topic. It covers all of science. We get a lot of interdisciplinary manuscripts which really don't fit anywhere else. Another thing is that it really is trying to connect the scientific paper, this kind of old-style way of communicating, with the rest of the online ecosystem. So you see, we can have notes and comments that people post on there, and user ratings where people rate, but also trackbacks. So when somebody writes a blog post, it's directly connecting to this paper, and the paper is connecting back, where we go to the whole thing of, the blogosphere, blogs, wikis, everything else is connected. The scientific paper is not going to be an isolated unit anymore. It's going to be interconnected with all sorts of other parts of that ecosystem. And I think, to finish, that in the future, a scientific paper, instead of being a discrete thing which has a date of publication and a place of publication, is going to be a much more dynamic process thing, where a number of different people are going to do different parts of the study and posting them online in real time, And then only in the end, you put all those pieces together and call them a paper. This is a study. So you don't have to wait until everything is done, then you submit, and then suddenly secrecy is over, you're open. I think it'll go dynamically over time. We're not there yet, but the next two people are going to tell you about the efforts to make that future come true. Thank you.
Thank you, Bora. That was actually a great introduction. I should always have you before my talks because you really covered the whole gamut of where we are right now. So I'm going to be able to go through this a little bit more quickly. I will be talking to you about one of the specific applications that Bora was alluding to, which is Open Notebook Science. So there's actually a definition now on Wikipedia, and if you're interested in links, articles, and all that kind of thing, you can go. But the idea is very simple, is that if you're doing research as an experimentalist in the lab, you keep a lab notebook. If you make that lab notebook completely public and as close to real time as you can, that's Open Notebook Science. So what that means is that you don't decide I'm going to share this experiment but not this one. And the reason for that is we really want to see how science happens, and we want to see the failures as well as the successes. We want to see the errors get corrected. We want to see how the whole thing happens. So that's basically what I mean by Open Notebook Science. Now, again, going back to some of the concepts that Bora was mentioning, we want to be able to track the provenance of the information as it goes through. And one of the things we forget when we read a journal article or a book is we start to believe what it actually says are facts, right? But any measurement, right, there's actually no such thing as a fact. Every measurement is embedded within assumptions. And if you don't know what those assumptions are, then you're missing out on information, and you don't know how much value to place on that piece of information. So with Open Notebook Science, we're maintaining the integrity of the data provenance by making those assumptions explicit. So, a very simple way to say it is we're going from a model of trust to one of proof. So if we see a paper, I know now in science we basically see, well, which group published this? I know that they've been reliable in the past. There's really no reason for that. I mean, I think that we have the tools right now. There was a time when paper was scarce, it was difficult to publish everything, but now we actually can communicate all this information. And in the experimental sciences, what you want actually is the lab notebook, because that is the absolute best record that the researcher is recording so that they themselves can repeat their own experiments. Let me give you a concrete example of how that can be used. So I'll be talking about solubility throughout my talk, and I'll give you a reason why a little bit later. But right now, let's say that we have this table, right, and we have all these data points. So this is the solubility of these different compounds in chloroform. And as a chemist, something looks really weird to me, because these compounds are really similar to each other. However, one of the numbers is extremely low, 0.07, where all the other ones are at least 1.75. So if this were in a table in a journal, what can you do really? All you have to do is say, well, I guess it's an anomalous compound. Well, with Open Notebook Science, you can actually ask the question, what is wrong with that particular number? So I will dig in to see how that measurement was actually made. So it turned out that was incorrect. It was remeasured at 3.6, which makes a lot more sense. But let's see how I could actually figure out that there was a problem. So if I go to the actual lab notebook page where that measurement was made, you see here in green is highlighted that at 9:30 they placed the vial in the speed vac and they removed it at 3:30. So it spent 6 hours under a high vacuum. And I know that that's enough to evaporate the compound that we were just talking about. The other thing you'll notice is that they did not record the vacuum pressure. They did not record the time they vortexed. So it's actually just as important to know what the researcher did not measure as it is than simply to assume that they did a great job and they did take care of every parameter. So this is the kind of thing that we want to resolve with Open Notebook Science. So there's a lot of parts of this. Just to give you a couple of examples, the other thing is that we can make the rationale of the findings explicit. So I show you the log portion, which is where the researcher records what they do and what they observe, and then they have to make sense of it, right? And so here, you can see what this particular research thought and why they're making the conclusions that they are, and they're linking to raw data, and they're presenting evidence. And the kind of raw data, as Bora said, we're not limited anymore with just text. So taking pictures of our evaporated samples, here's a couple of interesting things. All of these samples after evaporation look clean, except this one looks like it might have splattered. Is that important? I don't know, but if there's an issue with this particular measurement, I probably would want to see that done again. If there's not an issue with it, it might stay there for 2 or 3 years until, until we figure it out. But the point is that it's available to anyone who wants access to it. You'll notice also the sample on the left has a little bit of liquid in it. Turns out that that's not actually a very important contribution to error, but it's still really good to know about it if you see a problem. Other kinds of raw data, Bora had mentioned video. I love video because for exactly the reason that you mentioned, is that if the student is recording an experiment, they don't necessarily know what to note down. And with the video, you can take 15 seconds, just record what's going on in the experiment, the whole setup, and post it on YouTube, and I can see where the thermometer is, and that could be an issue. Maybe the thermometer wasn't in the solution, and then with the measurements, what do they mean? It changes. So I love video. Another thing that we use quite extensively are Google Spreadsheets. So these are documents that are totally free, totally available to anyone, and people can share and they can add information, they can comment. And the really nice thing is that you can make your calculations public. So if there's a number and I'm wondering if there was a problem with it, the first thing I'll do is I will look at the calculations in the spreadsheet. And it actually tells you every single measurement, when they weighed the vial, when they added the solvent, everything. So if there might be an error in the calculation, maybe they use the wrong molecular weight, that happens all the time, I'm able to make a decision. And the Google Spreadsheets also has a really nice feature. It has a history. So you can actually go back to a different version. If somebody goes in and changes a value, you can tell that and you can track all that. It's very similar to a wiki. So we also use wiki pages as our actual lab notebook. And there as well, every time somebody goes in, you can tell who it is that came in, and you can see when they actually made that change. And so if you're familiar with the wiki, basically it's just a program that's very easy for anyone to come in and edit it, and you have every version, and what you can do is compare 2 versions. So if we compare one version with the other, I can see in the green here, this is the new stuff that was added, and the red, that's the stuff that was deleted. So in this particular case, this was a question that I asked to the student, and when they answered it, they deleted my question. So that's actually a very good way to interact with students, because you can pinpoint exactly, ask them a question, and it's a great way to teach science. There's so much more that we can do with our technology. There's a format called JCamp-DX, and that will represent any spectral information that you can plot on an XY axis. And what you can do is use JSpecView, which is a free Java program, and you can just expand any area of this spectrum to zoom in to see the fine details. This is actually really important. This is an NMR spectrum. And what this shows me down here is that there are actually impurities in the sample. And oftentimes when you submit to a journal, you give them a PDF, and you can't always see exactly where the impurities are or how much there are. So this is really nice because you don't have to rely on the author to decide which section to expand. You can go in and expand it. And this is 100% free, 100% open, and there's no programming to learn because it's just Java. It automatically loads on your browser. There's so many other tools as chemists that we can use. Chemspider is one where basically it's a very large database, having maybe 22 million compounds, and I can link to compounds there. I can actually add my own data. If I measured a melting point, I can add that. If I took a spectrum, I can add that. And I can also do substructure searches within Chemspider. So instead of me having to worry about getting a programmer on my server to have my own customized applications for searching the compounds in my lab, all I can do is just put it in Chemspider and they're the experts in storing chemical information, let them worry about all that stuff. And again, this is a free service that's very, very useful to us. As I said, we can upload data. We've also started to upload these non-aqueous solubility measurements. So there's all kinds of things you can do. Now, when you upload a spectrum in Chemspider, it asks you if you want to make it open data or not. And I think a lot of people, when they first see that question, might not realize what's the difference and why it's important. This is the reason. Because what we've been doing now is took all of the open data spectra and we made a game out of it. We have actually 1,000 spectra. That basically, you have a spectrum that's given to you, and you've got 3 molecules. This is a collaboration with Andy Lang and Tony Williams from Chemspider. And basically, you just keep clicking on the right molecule until you get one wrong. So I'm actually giving a prize right now to the first student to reach 100 points. It's actually a pretty hard game. And this is what open data means. It's the difference between this and nothing at all. It's very important to think about it. It's very important to think about how maybe someone wants to use your data in a way that you have never imagined and don't even want to be bothered with. But it's really important because really useful things can be done. And we've also implemented this in Second Life. Don't have a lot of time to talk about this, but if anybody is interested, I've actually removed most of my Second Life slides because of time constraints, but I'd be happy to talk to you about it. Okay, so let's take this to another level. I've just shown you what happens if you have one group that's recording their work. What happens if you take this to the next level and you actually start to crowdsource it? And that's exactly what we've done with Solubility. So in the fall last year, started this Open Notebook Science Challenge. And the idea is very simple. It's just to invite anyone in the world to take a compound, pick an organic solvent, and report the solubility. It turns out that actually that information you would think would be widely available, and it's not. You can find aqueous solubility fairly easily. You can find the melting point of any solid out there. You can find the boiling point. There's all these properties that you can find, but one of the most important properties, which is I want to do a reaction in a solvent, what solvents did I choose? That's actually pretty hard to find. There are some measurements, but you won't find most of them. So we've got this challenge to make this all open. People can contribute, and we share it with everybody. And so there's also some sponsors that we got. Sigma Aldrich has contributed some free compounds. Nature contributed 1-year subscription to Nature magazine. For the first 3 winners. Submeta contributed cash prizes. So we've got 10 prizes, $500 each, 1 a month, and we've given out 3 so far. So there's still 7 to give out this year. If you know any students who'd be interested, any student in the UK or the US is eligible. So we've had, as I said, three winners. We've had Jenny Hale from Southampton, Khalid Mirza from one of my students, and David Bulger, he's at Oral Roberts University. So really spread across the world, and this is working out. And so the way that we actually give out the awards is we have meetings between judges, and the judges include myself, Cameron Nayland, Rajarshi Guha, who's a programmer, Tony Williams, who's an NMR expert, Bill Hooker, who's a molecular biologist. So all these people have completely different angle towards science, and they're able to evaluate what the student does, how they respond to their comments, and we come to a decision as to this student, in this period of time has probably done the best job. So I think this is a pretty good model, and I've been very happy to have such high quality people join it. And again, what else can you do with this? Once you have a system in place, it's actually not that difficult to take it to another level. So here, Brent Friesen from Dominican University just decided, well, why don't I make my first week of sophomore organic chemistry teaching lab to measure solubilities, right? He's got to do it anyway. He has to pick, he's got 10 weeks, he's got to pick certain experiments to do, and he just took the time to actually do a good job and ask the students in the first week to measure any compound in any organic solvent that they had available. And so, and he uploaded those data points, and we did get some new measurements. So if you imagine actually being able to leverage this across the world, every university has teaching labs. There's huge untapped potential here. It just requires the will to actually implement something different that you've been doing for the past many years. So how do you access these solubility measurements? Well, one way is through a regular table of contents. That will look just like paper. You can go to experiment 14 and you can see what Jenny did. But probably a more useful way is through a database interface. So we've used Google Spreadsheets as a database, and it turns out it does a really good job. So every time we have a measurement, we add it to the Google spreadsheet, and it has, this table is pretty large, it goes on, but it has the solvent. It has information about how to render that. It has information so that a machine knows that that's acetonitrile. It has the link to the notebook and everything. And Google actually has a visualization API that is really nice. So you can actually treat a Google spreadsheet like a real database. And you can do queries like pick a solvent, pick a solute, or pick a solubility range, and it will return exactly what you ask. So this is actually a really neat way to query this. And the important thing here is that this is live data. If a student does a measurement in the next hour and they put it here, and you do a search later tonight, this is live. So should you trust that number or not? Well, again, it comes down to being able to go all the way back through the chain of provenance. So if you look at, for example, vanillin in methanol, these numbers should all be the same because it's the same compound and the same solvent, but they're not. There are differences. So if you want to investigate and see, maybe one of those experiments wasn't done properly, at the bottom of the page, there's a link to the lab notebook page, and you can go in and you can figure out, I will include this or I will not include it. And lately, we've also been able to do substructure searching, which is pretty cool. So it means that if I want to ask the question, all the analogs of 4-hydroxybenzaldehyde, give me their solubility, I can do that by using what's called the smarts. And so this is actually really, it's quite a powerful database when you think about it. All kinds of things we can do. If there are any chemists in the audience, if you're doing drug development, you've probably seen these charts where you can take two molecular descriptors and you can plot, and in this case we're plotting solubility. If you were developing a drug, you would plot activity, assay results. But you can actually explore the chemical space, and again, this is all live. This is all done live off of that Google spreadsheet. You could also do the same thing in Second Life, and you got an extra dimension to play with. Okay, so again, I really want to drill this home, this whole concept of provenance. So what do we do with this information? Well, if you know about that little website, you can go in and you can use the drop downs and find your compound. But what if you don't? Well, we've started to add links from Wikipedia. So if you go to the benzoic acid entry, you'll see now that there's an entry for solubility. Well, there's always been an entry for solubility in water. Like I said, that's pretty commonly available. But now there's an entry solubility in, and then the solvents will vary depending on what we've done. But that link actually takes you to this. It takes you to this page, which shows you all the solvents, all the concentrations, gives you the standard deviation for each one. And then if you want to drill down and look specifically, for example, methanol, it will give you these 5 measurements. And then if you click on one of these columns, it will take you to the lab notebook page. And if you click on this, it will take you to the Google spreadsheet with the actual numbers on the scale, exactly what was measured. So this is what I'm talking about with provenance. Basically, you can track everything. And we can even include links to literature. We were talking earlier at lunch about the Google books. This is great. I mean, once they're out of copyright, you don't have to worry about how people are going to access it. Anyone in the world now can just click on a link. And the nice thing about solubility, it's a pretty simple measurement. So, a lot of it's been done 100 years ago. Unfortunately, they didn't finish it, but they did actually do a lot. So I can actually I can make one of the references just another data point mixed in with all the lab notebook pages. So now you can compare things and you can see what's making sense and what's not. We also have, if you also include temperature, our little, this is Andy Lang built this. It will basically give you the curves of temperature. So this we want to do in the future. Once we get a lot more people, we want to get a lot more temperature measurements. And again, in Second Life, we can explore solubility. This is kind of a neat explorer. If you click here on the different aldehydes and you stand on these, it's like an elevator. The higher the solubility, the higher you go. And you can see over different solvent systems where the different components are going to be soluble, where they're not going to be soluble. I don't have a lot of time today, but that's basically the idea behind this, is to be able to control chemical reactions and control when they precipitate. So the better we can visualize these things, the easier the chemistry is. Okay, I want to talk a little bit about this useful chem project that was mentioned earlier. So again, this is Open Notebook Science. This is prior to the solubility work. And the idea here is we want to make new antimalarial compounds. So this represents a collaboration between computational people, specifically Registry at Indiana University. He does docking. So he basically, we have a library of compounds, and we want to know which ones are most likely to inhibit an enzyme. He tells us, we make them, and then we ship them off. Phil Rosenthal at UCSF does the assays. He tests them. So basically, you have all the 3 components. You have the theory, you have the synthesis, and then you have the assays. And that's what you need to go through a full cycle of drug development. And we're working on the falcipain 2 enzyme recently. So the way that we spread these out, I've already shown you some of these components, right? I've definitely shown you the wiki. I've shown you the Google Docs. But some of these other things I'm going to show you in just a minute. And we can also use a blog, right? So how do we use a blog? Well, when we started this project, the idea was one experiment, one blog post. Well, that really didn't work out very well, because what happens is that the experiment, you know, keeps getting updated, and then the student writes a discussion, and then there's errors, you fix it. So it turns out, and the problem with the blog post is you can change all that, but you can't track it. So you can't tell that things were changed. So that's why we shipped, you know, that's why we changed to a wiki. But the blog is still really useful for giving, you know, milestone information to people about our project. And what we do here is we basically, you know, discuss something, and then we click on a link. So it says, see experiment 150. That takes us to the lab notebook page. You've seen this format, right? And the one thing I didn't show you earlier is you can actually put stuff that is not just synthetic chemistry. This is the docking results that Registry did. So you can actually track exactly the way that Registry did the calculations, and if you did it the same way, you should end up with the same list of compounds in the same order. So we want to make really everything reproducible. And so it turns out that we've identified 4 compounds that are reasonably active against malaria and against the diphosphopane 2 enzyme. And those results can be put in another database called Collaborative Drug Discovery, CDD. And here, if you're looking for assays for different diseases, that's another place. So you'll see every different kind of information has its own natural place to aggregate to. Okay, one last concept that I want to bring across here. So where does that put traditional publications? Because I haven't talked about that yet. I've just talked about there's a notebook. So here's a project where we have this reaction, we want to optimize it. So we're going to vary the concentration, the solvent, excess of some of the reagents. We're going to write a paper on this. So we wrote the paper on a wiki, open to the world in real time. So all the drafts are there. And the really nice thing about having a lab notebook that's open is I can actually say the melting point for this compound was obtained from experiment 99, but its HNMR was obtained from experiment 203. That's a little simplification that gets made in papers. It says we made this compound and we did these measurements. That's not really true usually. They might have made several batches. So here you're actually referring to the specific batch. So there's a problem down the line, you can track it back. So what we also did is we submitted that paper to a peer-reviewed journal. And Bora was mentioning Journal of Visualized Experiments, I think. So this is where there's a video portion and there's also a written portion. So the written portion obviously was what we wrote on the wiki. And then, so we got this paper accepted. And as the paper was under peer review, we also posted it on Nature Proceedings, which is a preprint site. So the nice thing about that is that, you know, we can actually talk about this article. We can talk about everything in it. I can give people an author list, a DOI, all of it. And then it gets published in Jove. That's great. And at no point in time did I have to, you know, that I wasn't able to give people an open link to my work. So basically, you know, who's doing this kind of thing? So here's 3 open notebooks I like to share with you. Gus Rosania's work. He's at Michigan. He does drug transport, both measuring and theoretical. Cameron Nayland, also, he's got some great presentations. If you're interested in open notebook science, definitely check out his videos. So he uses a modified blog engine so that you can in fact see the tracking. So it's a little bit different than our system. And a recent addition on OpenWetWare, actually, Anthony Salvagnos. He's basically just started a couple weeks ago, and he really has been putting everything he's doing up on there. So that's been really nice to see, and obviously he's doing some molecular biology here. And I think I mentioned most of these people in my talk, and that's it.
I should start by echoing the thanks to the organizers and Catherine Pope in particular for inviting me down here and setting everything up. It's been a fun visit so far. I'm going to talk about some of my own experiences with open science during the course of my PhD, and some of the initiatives that we started at MIT. And I may forget to note this explicitly on a few occasions, but I think you'll see there's a lot of common themes between what both Bora and Jean-Claude have previously talked about. So let me just... So I'm going to talk about my own specific experiences, so it makes sense to talk a little bit about what I did. So I'm going to give some definitions, and this is a sort of a limited definition of myself. I'm a synthetic biologist, is the sort of work I do. I'm now with a startup, Ginkgo BioWorks, and I've also been involved a lot with OpenWetWare.org, which I'll talk about a little bit later. So I want to explain just very briefly what synthetic biology is. Synthetic biology is a new discipline, and its goal is to design and build novel biological systems aided by an engineering infrastructure. So to split that sentence up into two parts, we're designing and building novel biological systems. For example, we'd like to reprogram bacteria to produce biofuels, drugs, or other valuable chemicals. And we'd like to do it through the use of an engineering infrastructure. And what that means is that rather than trying to engineer bacteria in a sort of an ad hoc fashion, as it has been the standard in genetic engineering and metabolic engineering disciplines, we'd like to use something more similar to the way electrical engineering works, where there's a lot of use of standardization, parts, computer-aided design tools, and we'd like to try and introduce some of those kind of tools into the discipline of engineering biology. So that's the kind of stuff that we've been trying to do. And the last concept I want to introduce is this concept of parts. And parts are essentially pieces of DNA that encode some sort of basic biological function. And if you take a bunch of parts and you put them together, and you put them together in the right order, you can use that set of parts to reprogram a bacteria to do something interesting. So that's sort of the means that we follow to try and make cells do new and interesting things. But we have some problems in this new discipline. The first problem is that this idea of biological parts, which we call biobricks, they don't currently exist. So we have to invent them. And we have to invent a means to describe them and a means to share them so that they can be easily reused by other people. The second problem we have is that a lot of people who are attracted to synthetic biology are engineers and computer scientists and people from backgrounds other than biology. And I was a mechanical engineer originally. And that means that we typically don't have the sort of the training, both practical and in the classroom, about a lot of sort of standard molecular biology techniques. So we have these two problems. And I think the second problem is sort of an interesting extension of what Bora was talking about earlier, where you have the problem where, because information has been sort of localized and hard to get access to, if you're at a non-major research institution, it's hard to get access to that information. There's another problem where even if people who are at major research institutions, if they're trying to change the sort of the discipline that they're working on, or they're trying to apply their technology to some new field, it's hard to learn about that new field. So there's sort of this general problem of information being constrained, and Bora did a nice job of explaining how we're moving away from that. So I'm going to talk about solutions to these two problems. The first solution that came out of MIT a little bit before I got there was the Registry of Standard Biological Parts. So this is a website which is essentially a catalog of these early collections of these biobrick parts that we've been making, people at MIT and people at other institutions. And it's sort of modeled on the Texas Instruments electronic device catalogs of kind of the 70s and 80s, where you could go and look up a particular transistor or a capacitor or an inverter circuit. So this is a website that's free and open and editable. It's a sort of a combination of a database and a wiki, where you can add parts, you can describe the parts that you've made, you can comment on other people's parts, all that sort of wiki functionality. And the Registry of Standard Biological Parts, as well as being a way to share information, it also maintains a physical collection of those DNA parts, and it distributes those to people who need them. So it's sort of a joint information and physical material distribution and catalog. And I'm going to tell you just two short anecdotes related to this Registry of Standard Biological Parts. The first is one of these parts that I was working on during my PhD. It's part number BBA F2620. It's a very simple little part that basically just lets bacterial cells talk to each other. It's like the receiver in your radio or cell phone. And it's not very interesting. Everybody knows how the biology and the science of this works, but it's very, very useful. The only problem is the traditional means of sharing information about something like this is through the published literature. And the journals tend not to celebrate small pieces of information that aren't enormous, new, exciting discoveries. So the means we chose to share our description of this part that we had engineered was via a data sheet. So this is the data sheet for BBAF2620. And we did a bunch of measurements on how this part behaves, and we put them on this data sheet. And it's intended to be presented in a form, and well, it's hard to see here, but it's intended to be presented in a form that if someone comes along and wants to use this part, all the information is contained on this data sheet so they can use it. And that's sort of different from having to trawl the literature to find out everything that you might need to know about a part. This is sort of a summary of this part and how you need to go about using it. And while we were taking all these measurements, this data sheet was evolving. It was online. It was both on the Registry of Standard Biological Parts, and it was also on OpenWetWare, which I'm going to talk about later. So we were putting all the data up as we were taking it. I'm not sure, I don't think we were as diligent and detailed as Jean-Claude described, and that was really nice to see. But basically, once we had data, it went up on the wiki and was available to people to use. And so eventually, we ended up publishing this work in a sort of a traditional journal. But we were able to include a pretty interesting sentence. A portion of it is here. And we said that we made freely available the DNA encoding BBAF2620 and its data sheet via the Registry of Standard Biological Parts. Already 18 higher order systems incorporating the receiver, which is BBAF2620, have been contributed back to the registry. And that's sort of unusual in the traditional publishing system, whereby the first people get to see of your work is when it appears in the journal. Whereas we were able to write in the paper, we've already been sharing the information and the physical DNA for this part, and people have been using it, and it's useful. And we felt that made the paper a much stronger document. We were already able to say that this is a useful object. And luckily, this sort of more traditional publishing house was very open to publishing stuff that was actually already available online. The second anecdote I want to tell is about something called the iGEM competition. This is an undergraduate summer competition where teams from around the world compete to engineer a novel biological system that's the most exciting they can do. And this is a picture of some of the teams who attended the jamboree at the end of the competition last summer at MIT. There's about a total of 70 teams of undergraduates around the world who work on this during the summer. And everything they do in the open. All the parts that they make, they have to contribute back to the registry. All their lab notebooks are stored on a wiki that's run by the iGEM organization. And they do everything basically in the open. And this might be a good time to show you one of those. And I think this is interesting because this is an undergraduate it's a competition, and it's research. They're doing new work, but engineered into the competition is sort of a pressure to be open. So, for example, there's prizes for who has the best lab notebook and wiki at the end of the competition. So it's a competition that has been sort of engineered to provide incentives to people who want to share information earlier. And so that's sort of an interesting. That's interesting because the sort of the current reward structure in science does not reward, or often does not reward people being open, or at least they think it doesn't. So here's an example. This is the winning wiki from last year. You can see there's information about the team. There's the calendar of what they did when, the parts they made and contributed back, pictures. They have a lab notebook where you can click on particular dates. I'm sort of picking this at random. Looks like that was a bad day in the lab. Let's see. Let's try here. Yeah, so they've kept a lot of their data online. I didn't pick a particular page to show, but on some pages you'll see they have sort of like gel images and all their data available. So anyway, this is a group of about 1,000 undergraduates every summer who are being trained to do open science and to be celebrated for doing that. So I think that's a pretty powerful story, and that's some of them there. So that kind of gets us onto wikis, and that was the next thing I wanted to talk about. So OpenWetWare is a wiki. You heard it introduced at the start. It's to promote sharing information among biological engineers. And we started this at MIT because even within our lab, we had problems sharing as much information as we wanted between each other. So we said, okay, we'll have a lab wiki, and we'll share information. This was back in early 2005. And then we decided, well, there's a lab we collaborate with at the other end of MIT campus, and we'd like to share information with them because they do the same stuff as us. So they came on, and then a couple of the labs down the hall also found it would be useful, and they joined as well, and it sort of spread organically like that, and quickly spread outside of MIT. And at this point, there's about 150 labs on OpenWetWare. There's over 5,000 registered users. And so let me just give you an idea of what OpenWetWare is. There's a lot of different things on it. So OpenWetWare has a lot of different content. One of the things it has is a lot of people keep their lab websites on there. So this is the Chrysanti lab from Imperial. You can see there's information about who's in the lab, their publications, pictures. They keep a lot of technical information on here, what restriction enzymes they use, their chemicals, how to do ordering, all those kind of low-level sort of things that make a lab work. So OpenWetWare provides it easy for people to share that sort of information within their groups. And they also keep descriptions of their research online. So you see a lot of things like that. There's also a collection of protocols that are edited by the community. People contribute them. So for example, Escherichia coli, there's a whole set of protocols that have been contributed by scientists from all around the world and edited by other scientists. The goal to come up with sort of refined, very reliable lab protocols that everybody can use. And this was really helpful to us when we got started because we were a group of people doing research that we hadn't been trained to do in some sense because we were spending a lot of time doing molecular biology. So to have groups come on here, contribute their protocols and their information made our lives a lot easier, and I hope it's making the lives easier for other groups who are getting started on new sets of experiments. Something else I'd show, there's also a lot of courses. I mean, it's a wiki, so you can use OpenWetWare for whatever you want. A number of people keep courses. This is a course run by Steve Koch, who Jean-Claude mentioned has a student who has a nice Open Science Lab notebook now. But he keeps all the information about this course and the interactions with the students online. They can comment, they can correct things, they can download the slides they need. So it's been a pretty powerful resource for courses, and there's about 10 or 15 courses on there at the moment. The last page I'd like to show you from OpenWetWare is the E. coli genotypes page. So this page started because one scientist was annoyed about how am I doing on time? Is that? This page started because a scientist at MIT was annoyed about E. coli genotype information, which is essentially codes to describe a particular strain of E. coli, and it's very hard to navigate. So it was started by a scientist, and then other people started to contribute to it. And it's now, if you search for any sort of combination of E. coli and genotypes or anything like that on Google, it's the first thing that comes up. And it's become a really useful resource for a lot of people, and it's been noticed as such. So if you look here on the left, you can see a list of contributing authors. So a lot of these people are sort of people that I've worked with at MIT. They're grad students and technicians in labs. But there's also people who have suddenly started editing this page, like John Wirtz, who maintains the Yale E. coli stock center. There's Mary Ross, who also works there. There's Peter Karp, who works at the BioPsych, which maintains a large database of all interactions within E. coli. So suddenly a lot of professors and people who work on databases are coming to a page like this and nucleating around it and adding a lot of really helpful information here. So that's a sort of a whistle-stop tour of OpenWetWare, and I need to move on. But just some statistics on OpenWetWare. We get about 4 million hits a month, about 100,000 of which are unique visits. We've over 5,000 registered users, and a lot of our pages are extremely highly ranked by Google. So this isn't open science in a really pure sense, where you're sharing every single piece of information that you do, but it's people are sharing the information that they're ready to and happy to share, and it's been very useful to a lot of people. So one thing I wanted to finish up with, an idea that actually Bora sort of touched on, which was that over time there's been this democratization of access to information. From Newton and his book that no one could get access to, all the way to everyone can start a blog and share information today. There's also been a democratization of fabrication, which is sort of happening more recently. So everyone now has a printer on their desk. They can print out whatever text they want. The next thing that's coming down the line are 3D printers that you have on your desk. So you can rapidly prototype a 3D object and have it on your bench. And the exact same thing is happening in biology. So we have a rapidly increasing ability to write sequences of DNA. And the reason I bring up this democratization of fabrication is that it means that information is becoming critical. If you have access to the information you need to do something, you probably have the tools to make it happen. So a sort of a striking example of this was about in 2005, the complete genome sequence for the 1918 flu was published. And quite shortly after, a second paper was published, this one here, in Science, where they synthesized that genome, the flu genome, and they got it working. They basically booted up that virus, and they showed that the virus has the ability to replicate in the absence of trypsin, caused death in mice and embryonated chicken eggs, and displayed a high growth phenotype in human bronchial epithelial cells. Basically, they made one of the worst pandemic viruses that we've had in our history, and they showed that it worked. And why were they able to do that? They were able to do that because someone had shared the information of the DNA sequence, and once that was out there, it was easy to make this and do it. So I bring this issue up because if you can share information, people will start doing a lot of things that are either good or bad, and there's a number of different ways we can choose to deal with that. The first is, you could say, if you want to do something like share the sequence of the 1918 flu, you shouldn't do that. That's going to be regulated. It's going to happen in a federal lab. Or a second approach is, you can say, which is what we do now, we say you can do that work and then you have to publish it in an academic journal. So the information only gets out after the event has happened, after someone has made the flu virus. The third approach is that if people were adhering to a sort of an open science approach and they were discussing their work as they planned it and as it happened, then people would be able to comment on work like this, where people are making dangerous flus, and would be able to either decide how to respond to it or whether to try and get these people to do something different. So that's another option. The current option is nobody talks about anything until after they've done it, and that can be a dangerous thing. So that's all I wanted to say. And just to summarize, open science can work. It's worked in my own case, and that might not always be true. I've been lucky in that I work in a discipline where it's relatively accepted. And finally, information distribution is becoming increasingly consequential, because once you have the information, you can do a lot of things. So thank you very much.
I noticed that most of you have Google products in your lineup of ways for your solutions, and you're talking about information being open. Personally, how do you feel about Google's presence with holding information, and how that's going to interact with your hope to open up science?
Google's everything about Google.
You have practical experience, I think, right?
Yeah, I mean, I love Google. I mean, Google's permitted us to do things that otherwise, would have been very expensive to do. I mean, the reason that I use those specific tools is because I want if anyone's interested in any part of what we're doing, that overnight they can replicate it. And so if we use a Google spreadsheet, I know for a fact that that will scale. We can get, you can use it immediately. Google's been pretty good overall. I mean, recently there was the Google research docs that was supposed to happen and then they didn't. That's unusual. I mean, usually, they keep improving it. But again, these documents, if down the road Google decides to not continue Google spreadsheets, it doesn't really concern me. I mean, basically, we can move it over to another platform. And at that point, if we have to buy something, we'll do it. But I think that the trend is to have more companies make available these kinds of platforms for free rather than going backwards. I don't know what you guys think.
Yeah, I mean, we use Google Spreadsheets a lot as well, not in quite a sophisticated a way, but we find them really, really helpful as a tool in our lab. So for the moment, we're trusting them. So.
Thank you very much for the presentation. I enjoyed the presentation, but I have a fundamental question about whether these projects are scalable to being the core of mainstream science. I mean, it seems to me that, I'm not an economist, and if there's one here, I'd appreciate his comments on this, but it seems to me that currently the economic infrastructure of science is based on the holding of private information by competitive agents in a large science marketplace that competes for funding. And I don't understand how this system is, I mean, what you're talking about is to subvert the entire funding distribution system of science. I mean, it may be much more subversive than you realize.
Yes, this is very subversive. The different areas of science are responding to this differently because of limited resources, how easy it is to replicate somebody else's work. So I think, and what are the possible rewards is patents, money, fame, Nobel Prizes, stuff like that. So the secretiveness is the greatest in areas where it's easy to scoop and where the rewards are potentially really big, where expense of doing stuff is big, and where there's a lot of competition. Think cancer research. They're not going to say anything to anybody. But there are other areas which are much more open. Let's say ecology. You have already 10 seasons of studying white-tailed deer in your corner of the forest. Who is going to scoop you? And you don't see their tent in that corner, and you're 10 years ahead of them. Much easier to share, much easier to do something like open science, because you don't really have competition. You can't be scooped. And there's no Nobel Prize for ecology. So then you have something in between, like dinosaur paleontology. 5.5 people have the money to do it. But once you go to some god-awful place to dig it, everybody knows you're there. Nobody's going to scoop you. You can absolutely freely take pictures of your fossil as you're digging it out every day. And nobody can do anything about it. You can't be scooped. You're the one who dug it up. So different areas are going to be different about it. So I think it's going to go in at different rates. The adoption of some or all of these opening kind of ideas of ways of doing stuff are going to be adopted at different rates in different areas of science.
Yeah, I mean, you bring a couple of different issues. In terms of funding, I think it's actually very good for funding. I mean, the last funding that I got was precisely because of being open on one of our networks, FriendFeed. And we've been publishing our proposals, and other people have been doing. Steve Koch is another one who's been publishing his proposals. And that attracts collaborators. I don't think that the federal agencies are going to look down at sharing. In fact, I think it's going to be positive. Now, where there might be an issue is in the intellectual property sphere, and I definitely agree. I don't think you can both pursue, at least in my case, open notebook science and intellectual property. You have to make a decision, but that's nothing new. I mean, when you decide to publish a paper and not file a patent or provisional patent or whatever you want, you've made a decision, so you're just making it earlier in the process. And so, as Bora said, it's different areas. I work in malaria specifically for that reason. I didn't work in malaria before I did open science, totally different. I'm doing that because it's a project that it makes a lot of sense to be open about. The solubility project, again, I think it's a very good area because it's easy to do, people can share it, and everybody can benefit. So I think, instead of, you might end up collaborating with someone who might be your competitor in another world. I think that's what we're finding.
Let me give you a related but different experience. I'm not in the lab anymore. I haven't been in like 5 or 6 years anymore. That doesn't mean my mind is not a scientific mind anymore. I have ideas. I just don't have a lab to do them. About 3.5 years ago, I posted a hypothesis on my blog. Okay, it's like, okay, if anybody's interested, you have resources, go do it. I would really like to see this hypothesis tested. There's no way I can do it. I'm now blogging and writing and doing other stuff. I don't have a lab. Well, 3.5 years passed, and I get an email out of the blue from, Cornell. We would like to test your hypotheses. I said, go ahead, just, once it's published, just let the people know where the hypotheses come from. I would like to see my name in print. As much as that. And I said, no, we want to collaborate with you. We'll do the field work, you analyze the data, and we write a paper. And I said, yeah, of course. I mean, why not? I can do that.
Yeah, I think we've seen similar sort of things where being open has led to new collaborations and new connections with people from people who have a different skill set than you. And that those collaborations can lead to very traditional forms of academic reward, like papers and funding. OpenWetWare, for example, has $1 million in NSF funding. So the traditional structure is certainly open to these sort of ideas, I would say, or increasingly so, at least.
Thanks, everybody. This has been great. I'm really enthusiastic about all this, and I'm going to throw in this wild concept that this all goes back to Marshall McLuhan and the medium is the message. The reason science is changing is because the distribution mechanisms for information have changed. None of you addressed what I think is probably the weakest part of contemporary science, which is the review process. In fact, what I've seen is that people don't have time to do adequate peer review, and they don't have the motivation to do adequate peer review, and that one has the experience of submitting hard work to peer review and getting reviews back that make no sense, and having very little recourse. And I wonder if any of you have any ideas as to how the existence of this new bidirectional communication medium will change the way things move from informal hypothetical science to formal peer-reviewed science.
Big question. You want to tackle that?
Yeah, I mean, I'm sure you have a lot to say, but for me it all comes down to the proof versus trust. If you give enough proof, you don't really need peer review for what you think you're doing. I mean, people think they submit to peer review and everything that gets put in that paper gets carefully analyzed, and we know that that's not the case. But instead of that, if you make people actually give in full details all the proof, then at a time in the future when someone tries to repeat it or someone tries to use it, then they'll be able to go in and find it. No one's going to be going through every little piece of detail during the part of the submission. So yeah, we didn't talk much about peer review. I mean, peer review is certainly compatible with Open Notebook Science. Now you have to choose your publishers, not necessarily, it has to be a publisher that will accept preprints. Luckily there are enough that, it makes sense in most fields. And
yes, and that's one of the important parts of what we talk about at PLoS headquarters every day, because it's a big deal. So asking for raw data, asking for videos and stuff like that helps our reviewers review better, because hopefully they'll run the simulations themselves or something like that. It's probably not going to happen all the time, but they're going to do it's just the first level or first layer of review. But then as time passes and people try to replicate or build upon those papers, and if something doesn't work, that's why we have those comments and notes. So 20 years from now, if somebody comes back to one of our papers, they're not going to trust it just because it was published in PLoS. They're going to read a paper, but they're going to read 20 years of comments and notes, additions, corrections. They're going to then see how much that paper can be trusted because of this whole post-publication peer review, which right now happens behind closed doors in the lab, offices, at meetings, corridors. It's going to be made public, so over time people will see how much to trust each paper.
I don't have a microphone anymore, but I'd like to follow up.
No. Just speak loudly. It's all right.
1, 2. Oh, okay.
Good.
My follow-up is that you still didn't address the key is that careers advance on the basis of publication. Now, I can blog until my head falls off, but that's still not going to advance how I look on paper. And it's the functionality of other people officially saying that I've done something valuable. That's actually the whole enterprise is the whole scientific enterprise is based on that. And so my question is not just the value of what goes out there. You've made a very good case for that, but how the validation will occur so that essentially so that grant agencies have better information as to who's actually doing good work and who's just cranking out papers.
Yeah, this is the problem of living in a age of transition where you have simultaneously two generations. And when I say generation, I don't mean age, I mean mindset. Secretive versus open, and they're going to clash. And that also means how you evaluate the quality of contributions of others is going to be very different in these two parallel worlds. And it's happening everywhere where internet is having the effect. Look at journalism. Newspapers are dying left and right. What is a trustworthy source anymore? Somebody who was on the Denver flight that had trouble taking off, twittering, hey, I was just in an air crash, or the journalist who a day later said, hey, there was a crash in Denver, that's what CNN said, and so I'm copying and pasting. So these kinds of questions are not solved. I don't have the answer to your question right now, but I think as the generational kind of switch happens, that all of these contributions that are outside of just, okay, I'm publishing in Science, Nature, and PLoS Biology, and so I'm brilliant, that all these other aspects of contribution to science are going to be evaluated in some way, because it's going to be evaluated by the same people who are doing it themselves. Kind of the Facebook generation is going to be judging the Facebook generation, not the oldsters judging the Facebook generation. So I think there will be a system evolving over the next 10 years, 20 years, that is going to then settle down into something that works, I hope.
I think I see evidence of that in my field already. For example, if you were a graduate student, there would be graduate students who could get postdoc positions in top labs, in top universities, based not on their publication record, but based on their record in something like the iGEM competition, advising undergraduates, or contributions of their own parts and materials to the registry of parts, or activity on email threads and mailing lists between faculty and students. So that's at the kind of graduate to postdoc level. When those postdocs end up on faculty hiring committees, pretty much as Bora said, I expect that they're going to take into account much more than just number of publications.
But in the meantime, keep publishing in traditional journals. This doesn't really stop it. It just affects a little bit where you send your stuff to. Mm-hmm. But no, I agree. I think in fact it's exactly the reverse is going to happen. It's going to be dangerous not to be open at some point because you're going to lose visibility. I mean, once you start doing it, it's so obvious that it's the right thing to do for finding people that, but right now you're right, we're not there. Definitely.
Yes, you're losing visibility, you're going to lose credibility. I mean, back to Facebook. Everybody's nervous. Oh, you're putting, your pictures of, drunken parties on Facebook, and when you're, up for a job and they're trying to hire you, you're in trouble. Yes, because the people who are hiring are not the Facebook generation. 20 years from now, if you don't have drunken party pictures on Facebook, you're a suspect. You are embellishing your profile too much. That's going to be suspicious. It's like everybody has those pictures. Where are yours? What are you hiding? And I think that's going to happen in science as well. Why weren't you open? Why were you hiding?
All right. This is kind of along a similar bent. Sorry if it perhaps seems a little bit redundant, but I think many of the concerns about open access publishing, and it's already been mentioned once, specifically revolve around tenure and how academics in the university setting view open access publishing as a credible record of your research, et cetera. And I personally don't have to worry about this for another 40-odd years, but I'm writing an article on this. I was wondering if I could get your perspectives on any situations you've run into, or if you have any other opinions.
Well, I work for an open access journal, so I'm assuming the question is for me. Okay, let's say right now the work is, your scientific output is measured by in which journal you published. It's not going to happen in 2 years. That's going to be gone. But right now it is that situation. So you're looking, okay, well, I'm publishing in Nature or Science, or whichever journal you can publish your stuff in. It doesn't matter if it's open access or not. The fact if that journal is open access or not has nothing to say about the quality of the journal or the quality of science in it. And yeah, people, there are enemies of open access because there are people who are making a lot of money on keeping things closed, and they're very good at disseminating disinformation. Open access has nothing to do with quality. Open access has to do with openness. The same paper in this journal or in that journal can be for pay or can be free. So I don't think, it's not just that I work for PLoS, I have to do my PR, but I go around. One of my jobs is to observe what blogosphere is saying about science and publishing and about us, the PLoS, and to make sure. So I've been in tune for a couple of years at least, and what people are saying. Say, well, you need to publish in Science, Nature, or PLoS Biology. What? Science, Nature, or PLoS Biology, and you're good for tenure. Science Plus Biology or Cell, or there's 3 or 4 journals that show up. One of them is open access, and nobody gives nobody gives any question. Well, one of them is open access and the others are not. Those are quality journals, and that's what is accepted internationally everywhere. Those are journals that you have to publish in if you are in these very competitive fields and you want to get a job at Columbia or Harvard or MIT. If you want to work at NC State, you're fine in some other journals. In a few years, when different measurement evaluation systems get developed and impact factor dies, then it won't even matter where you published your paper, because your individual papers are going to have their own measures. And the tenure committees are going to look at the measures of your papers and not the journals in which you published them.
Well, the committees are also looking at your reputation, which is based partially on your publication in different journals, but also based on your activities in the community. So I think that's where it comes down to. I mean, the letters of recommendation and what people will say, I think that factors very strongly. Of course, if you have no papers and you have a great reputation, that's not going to work. But if you have some minimum number and you have a great reputation, and that's really where the thing comes together. But yeah, Bora mentioned something really interesting, which is the miscommunication about open access. I mean, there are people who still think that open access means there's no peer review. and it has nothing to do, with it. So I think part of it is, we have to keep going out and repeating the message. Well, you do, for sure.
Yeah.
And, I think people will get it. It's just a question of using it and, handing your paper over that you've published in an open access. And they're very addictive, because once you've got it in this open access journal, you can share it with anybody, and then you go back to one of your older publications, and you can't do that. It's really annoying. So once people start to experience it, I think it makes sense.
Yes, it's a gradual process. I think it's going actually faster than people who started the open access movement have envisioned. I think scientists are in generally, they might not know, they don't know exactly how to go about it, but I think they viscerally like the idea of openness and are receptive to the message. They can hear it once. You don't have to repeat 30 times for every person to show them the benefits of publishing in open access journals or depositing in institutional repositories.
This, it sounds all in theory very nice and utopian and equitable and everything, but I still would like to, it seems to me from what you're saying that open access, there are certain fields that lend themselves more to open access than others, and that as this progresses, there will be certain areas that go that way and certain areas that continue, in the old tradition. Now, one of the things I'm thinking about is there's a lot of collaborations between universities and companies. And obviously, there's where you're going to have your real secrecy. Is there a utopian vision of any changes in that could open that up? Is that possible? Or, this is going a bit far afield, but, I'm just curious if you guys have any ideas about that.
Yes, we are, if you read Tolkien, we are the open access nostril. But I have to say something. Open access, especially open notebook science, what they're doing is not for everybody. There are situations where this is not an advisable thing, and that is, for instance, R&D, defense, things like that. No, you want to keep those things secret. It's government research. We're building a new rocket. You don't do open notebook science on that, and that's fine. And there are going to be other kind of in-between cases. So we're trying to push those people who are in the areas that should profit from doing it openly. But we understand, I think you agree, that there are areas for which that is just not the appropriate way to go.
Yeah, I would even say that, I don't foresee mainstream science becoming open notebook. I don't see that at all. But the beauty of it is that you only need a very small fraction of scientists to actually do it to gain the benefit. And that's really what we're shooting for, is to not necessarily convert people, but to find people who recognize that, hey, I'd like to do this, but I don't have time to figure out how, so show me how. And then we have the how now. It's just a question of doing it. See, the nice thing that happens, especially with open notebook science, is that the day that the experiment gets done, everyone knows about it. So a stranger could come and pick up your project that very same day. And that's really why I keep making such an emphasis on this concept, because if you delayed your notebook by 6 months, you lose pretty much most of the advantage. It's at that point when I think we're going to start to see machines collaborating with machines on a very, very rapid basis. If you can read and write for free on a platform, then you can start to think about these things. But no, you absolutely don't need to have mainstream science become that. And people who have their livelihood dependent on patents obviously can't do that at all. And that's fine.
Yeah, my experience, I've transitioned from an academic community that kind of viscerally supported like open access to information, and now I'm working at a company, and we've had to accept the fact that if we're going to stay in business and make money, then there are things that we have to keep proprietary and keep to ourselves. So I think there's just different solutions for different groups, even within science.
Or if it changes, it's not going to be very soon. It's going to be in 50 or 100 years, science fiction kind of, with technological changes, you might get to the point where it's fine for a government to build a new weapon and do it openly, and nobody can do anything about it because they're still the fastest. They started first.
Yeah. Well,
But not
obviously,
now.
there are issues of national security and things like that where you absolutely, secrecy isn't even a question. But something like the pharmaceutical companies, which fall into the ethical gray area, because if you're trying to develop a drug for malaria, obviously, for the good of the millions and millions of people who are dying from it, it pays to collaborate. It would be wonderful to have everything out in the open.
Yeah.
And this is a huge debate within the pharmaceutical, science area. And my question was more towards those gray areas rather than, the obvious areas where, national security would be compromised.
So you're by the sound of it, you're probably familiar with some of the things the pharmaceutical industry has been doing, where they've been declaring certain pieces of information to be pre-competitive, and they'd prefer to just have them out and open and shared between everybody. So I think it was the library of SNP data that some of the big companies decided, well, we should just share this with everyone. So you do see some examples of that, I think.
And I think solubility falls in that area too. That's something that all companies could benefit from, and it's so general that they couldn't really gain any competitive advantage. So yeah, and there was some discussion of this at SciFo actually, right? There was a couple of sessions where, because each company is spending all this money doing the same thing, and it's not necessarily competitive. So, yeah. Probably not, but I don't know.
Probably not. They should have. Maybe they would survive. Did they?
It's a similar level concept, yeah.
But I'm assuming they're pretty good at reverse engineering Toyotas, so figuring out how they work so they can build something better, maybe. I hope.
Because I heard at one time that a lot of engine things are shared. Like GM would make an engine segment or part of it. And it would be in a Toyota car, or maybe Peugeot, and things like that. But I don't know if that is actually open culture, the internet, or sharing on that.
Well, that would be the parts culture that you were talking about.
Yeah.
Yeah, I mean the sort of the parts culture that grew up around electronic engineering. You still have to pay for access to things, but things aren't secret, and the amount you pay is typically small because you want to get lots of people using your parts basically. So it doesn't make sense to follow the sort of the biotech model where you patent something and you charge the hell out of it if anyone wants to get access to it. So there's definitely in some industries a trend towards getting a very small amount of reward for a lot of stuff rather than overly protecting.
I have a question about the community aspect of your projects. I'm probably not the only one here who has managed a general interest online community before, and as a longtime contributor and administrator of Wikipedia, I know that a lot of work goes into what you might call the behavior management aspect of an online community. And I was wondering, you might not have run into this yet, depending on how much the projects have scaled and what types of audience you're getting. But have you put any thought into how you're going to manage some of this community structure aspect of the projects?
You mean for bad behaviors?
Not necessarily bad behaviors, but in terms of instituting a culture within the project of what types of collaborations are expected, what types of behaviors are acceptable, where the boundaries are. Do you have administration within your project?
Well, that's kind of interesting. I didn't talk about that because I didn't have enough time, but there are certain tools that you can apply now, like there's the Mechanical Turk at Amazon, where, for example, I've used it to format the columns in one of our spreadsheets. So if the students forget to capitalize or to not capitalize the molecules, I can just apply that Mechanical Turk it costs me 4 cents, and it's done. And you can do that repeatedly. How many of you are familiar with Mechanical Turk?
Those are people.
Yeah, those are basically people.
They're not machines.
Where you send out instructions and people reply to it and they execute those instructions. And we've coupled that with Google Spreadsheets in a very nice way. Now, you can't do very sophisticated things with it, but what you're talking about, which is, ensuring norms and formats and things like that, you can use things like that if, you don't have enough people to manage. But yeah, I mean, the culture, look, when we have a Google spreadsheet, we let anyone edit it, but the email goes out as soon as it gets edited. So once in a while, somebody will come in, they'll delete a cell because they don't know what they're doing, and that's fine because we get an email and we go in and we go back to the previous version.
Fix it.
So what happens if people, 100 people do that a day? Then obviously we'll have to change the way that we do things. And I've done that with my blog, going from having no controls over who comments to putting a CAPTCHA, and finally admitting that I had to moderate the comments because there was just too much spam. So you keep going on and on until you reach that equilibrium.
Yeah, the community on PLoS journals, there's always this question how much commenting is going on there, a lot or not. You're probably familiar that Nature tried experiment on that, which lasted 6 months, and then they shut it down and said it didn't work. And I looked at that and said, well, it's too early and it's too short. So when I was hired for PLoS, and I said, can you get it to the 6 years in 6 weeks? I said, no, give me 5 years. I said, oh, okay, I want to do some other stuff in the meantime. So sure. So it is going to take a while. It's the PLoS 1 is now about 2 years old. Last week is the first time I had to delete a troll comment. They're starting. It's getting there. UNED just did a big analysis of our commenting. We're doing better than BMC journals. It's happening, but it's going slowly. And I'm trying to keep my bosses happy by doing other stuff and telling them, give me 5 years. It takes time. On the other hand, on my blog, pretty much all I do all day is deleting troll comments. So depends on the topic. We have some on purpose, some not on purpose, difficulties on throwing things on PLoS 1 papers. You need to go through a registration process, which a lot of people are grumbling about. It's not easy, but it makes it really hard for trolls and spammers to post stuff. So it's, you have to balance it. You want to deter those who you don't want there and still get people to post comments. It's a fine line. We're constantly experimenting with kind of how much difficulty it has to be for people to, and how much ease for people to actually participate. And it goes, which paper, how controversial the topic is, how interesting the topic is. And I also think of those things that, a PLoS 1 paper is not a blog post. When I write a blog post on my blog, I expect all the comments to happen within the first 24 to 48 hours, and then that blog post is dead, pretty much. When I think of PLoS 1 paper, I think, okay, it was published today. I'm interested in all the comments that are going to accumulate on that paper over the next 20 years. So it's a very different way of thinking, and a lot of people don't think that way. But I like to give like a historical thing. Can you imagine if PLoS 1 existed, what was it, 60, 70 years ago, when Watson and Crick published the structure of DNA? Can you imagine if there were, ways to put notes and comments on that paper? And can you imagine 67 years later, reading all the notes and comments on that paper? Well, that's the text. That's what you do when you have a new student come to your molecular biology lab. Here's the history of your field. Read the notes and comments on the Watson-Crick paper. That's the history of molecular biology. Historians would love it. Molecular biologists will love it, and you see exactly how it all works. So I'm thinking of those in long terms. It's not a blog post. It's just the beginning of a much, much longer process.
One thing that we did very early on with OpenWetWare was we decided that so anyone can read it. It's readable by the world, but we wanted it to only be edited by people with accounts. And we set it up such that if you want an account, you need to use your real name or what looks like your real name, and have a real email address and some sort of affiliation. And if you're not affiliated, then explain to us why we should let you on and why you're interested. And we think that's helped a lot because you're not an anonymous person. You are who you're supposed to be when you're editing the wiki, and all your edits can be tracked. So we think that having it be real people, attributable people editing the wiki makes a big difference. And to echo what Bora said, over 4 years, I think we've probably had to edit about 3 things that were written on the wiki that were inappropriate for one or other reason. So.
Yeah.
That's 5,000
also,
users.
this depends a little bit on your reputation. If you're a single blogger or a very small community, the trolls are going to be much bolder. Attacking PLoS is not something that's taken lightly. It's a big institution. And if you're a troll, you probably assume that you're going to be deleted, and that you're going to, you're attacking too strong a target. And creations and those, they're cowards. They're not going to post comments on our papers. They don't do it.
We also require that people log in to edit, but it's for a totally different reason. Is because my students kept forgetting to log in, so they wouldn't get credit for the stuff they did. But yeah, essentially it's the same model. It makes a lot of sense. Everything is free to read, but to edit, you just have to register.
Yeah. I mean, the idea is just like when you're publishing papers, you have your publication name that you always use so that you get attribution for that. And as a result, you want it to be good. And we think it should be the same when you're editing stuff online. So.
Mm-hmm.
Hi, I had a quick question. How, or maybe do you think the practice of open science will change in response to recent legislative actions? I'm thinking of the increase in funding for the NIH and the NSF in the stimulus bill, and also the appointment of Obama's Science Advisory Board.
Yes. I mean, who one of his advisors is, Harold Varmus, who unfortunately could not be here today because he's traveling around the world. He's a busy person, always been, and he is even more now. So I'm hopeful. I don't know. I have no information on any specifics. I'm glad that some of the money got saved for science that was initially deleted from the stimulus package, and then about half of it was brought back. So there's going to be some money. There's going to be some very interesting, forward-looking people advising Obama. Obama mentions science is like every week in his speeches. So I'm optimistic, but I have absolutely no individual pieces of information, anything I can say to directly answer your question.
I mean, a president who uses a BlackBerry after one who didn't use email, I think it's got to make a difference. So.
Yeah, it's got to be better.
I'd like to thank Bora, Jean-Claude, and Barry for a really fascinating set of presentations. I think this video would be interesting to look at in 5-10 years' time to see how many of these predictions have really come true, and it may be a really fascinating point in time in the real expansion of open science to have this conversation today. So very much appreciate all of you coming. Please watch out for our next announcements of other sessions, and look forward to seeing you at other events. Thank you so much.
Thank you.
Thank you.